Okay, so we're gonna now talk about the second part of this series of videos about capacitors is capacitors in circuits. So we're going to talk about two different situations, um, capacitors in parallel and capacitors in series. So as I mentioned, next week is a full sort of like coverage of circuits, and we'll talk extensively about the difference between parallel and series. Um, we're going to just define it very simply in this video, like the difference between parallel and series, but we'll get like much deeper into it next week. So don't worry so much about like parallel, like the definition of parallel versus the definition of series. It'll become much more clear next week, but I think it is worth talking about capacitors in this context since like this entire week is about capacitors. Okay, so let's just like first draw out what the simplest circuit might look like with a battery and a capacitor. And then I think that will help you see like what it means for something to be in parallel. So let's just draw a little sketch of a battery, a circuit with a battery, and then connected to a capacitor, a parallel plate capacitor. Okay, so it's going to look like that. So remember, this is the symbol for a battery. So the long line represents the positive terminal of the battery. The short line represents the negative terminal. And then I've got it just connected to a parallel plate capacitor. Okay. Now, remember last week we defined this term equipotential. So let's say this is a 9-volt battery. Right? What this actually means is that the potential difference between the terminal, the positive terminal, and the negative terminal is 9 volts. Okay, so equipotential, we can say that everything connected to the positive terminal, so like everything along this path, this like green dotted line, including this top plate in the capacitor, everything there is an equipotential. It's an equipotential surface. And everything along that path is at 9 volts. Okay. On the other terminal, on the other side of the battery, so like this, the potential difference between the positive and the negative is 9 volts. So we could say that everything along this equipotential, there's another equipotential surface here, is at 0 volts. Right? So the potential difference like across the terminal of the battery is 9 volts. And it really doesn't matter whether we say like the low potential side is at 9 volts and the high potential side is at 18 volts. What matters is that the difference between the bottom and the top is 9 volts. Okay, so like if I define the top like along this green dotted line as 9 volts, then along the red dotted line has to be at 0 volts because it's the difference that matters, as is always the case with voltages. It's the potential difference between 2 points that matters. Okay, so when you connect a capacitor to a battery in this way, basically what happens is charge flows from the battery to the capacitor until the capacitor is at the same potential difference as the battery. Okay, so there will be like a charge will flow basically along here, right? And there will be an accumulation of like so like I should make these like so charge will flow here like along, right? And I mean you can conceptualize this in different ways, but let's just say like that negative charge is flowing to the negative or to this side of the capacitor and positive charge is flowing to the top plate. Okay, and that will happen, like that flow of charge will occur until the difference between the two plates is also 9 volts. And then the charge will stop flowing. Okay, and both the battery and the capacitor will both be at a potential difference of 9 volts. So like the difference, like once this plate becomes like an equipotential line with the positive terminal of the battery, charge will stop flowing, right? Because charge only moves when there is a potential difference between 2 points. Okay, so the capacitor, so like what will this do in answer to this question? The capacitor will charge up, capacitor will charge up until the potential difference across it, across the capacitor, is the same as the potential difference across the battery. Okay. And at that point, the charge will stop because like you'll have like two basically like equipotential surfaces where like everything on the top is at 9 volts, everything at the bottom is at 0 volts. Okay. So let's say that we have a circuit with two capacitors, C1 and C2, and they're both in parallel, okay, with each other. What can you say about these capacitors? Well, they have to, by definition, have the same potential difference. Okay, so like let's draw it out. So let's say that I've got a battery again at 9 volts, and I've got that battery connected to two capacitors in parallel. Okay, so this is a 9-volt battery, which means that everything along this path, like everything along here, everything connected to this path has to eventually be at 9 volts. Okay, so it's like 9 volts here, 9 volts here, 9 volts here, right? And then once this plate gets charged up, that plate will be at 9 volts. Okay, and then similarly down here, like on the other side of the battery, this would be at 0 volts. Okay, so the potential difference across C1 and C2 would equal the potential difference as the potential difference of the battery. So the potential difference across C1 has to equal the potential difference across C2. Okay, has to equal the potential difference of the battery. Okay, so all three of these things are equivalent when you have a situation of capacitors in parallel. Okay, so now we're going to sort of like talk about how would you make an equivalent capacitance. Like if you wanted to figure out like how do capacitors add when they are in parallel, we're basically asking the question like how could you reduce two capacitors in parallel down to a single equivalent capacitor? Okay, so let me draw the same situation as I had in the previous question. Okay, so this is like C1 and C2, and this is a battery. Okay, let's say again of 9 volts. And I want to like, I want to draw, I basically want to reduce these two capacitors down to a single capacitor. And I want to sort of figure out how I could add them together. Like in what mathematical like operation do I need to apply in order to get an equivalent? So this is what we're gonna call an equivalent capacitance. Okay, so like this would be like combining C1 and C2 into some equivalent capacitance. Okay, so the question is, how would we do that? So let's start out with the definition or one of our definitions of capacitance, which is just the charge divided by the potential difference between the two plates. Okay, so I can rearrange that and say that this is just going to be Q times, or Q equals the capacitance times the potential difference. Okay, and the equivalent charge on this equivalent capacitor would just be the sum of the charge from each of these two plates. So it would be like however much charge is on this plate plus however much charge is on that plate. Okay, so to get sort of the equivalent charge, you would just sum up the charge on each of the two plates. Okay, so now what I'm going to do is substitute this equation into this like basically sub 1 into 2. Okay, so I could say that the Q equivalent is just going to equal C equivalent, which is what I'm trying to figure out, times the potential difference, right? Equals C1, so the capacitance of capacitor 1 times the potential difference, plus capacitance of capacitor 2 times the potential difference. Now I know that these three, the delta V's are the same by definition. Like by virtue of the fact that the capacitors are in parallel. Okay, like they have to be the same. Like the potential difference across this capacitor has to be the same as the potential difference across the battery, has to be the same as the potential difference across the second capacitor. Okay, so therefore I can cancel out these delta V's, and this reduces down, this formula just reduces down to the equivalent capacitance is just equal to the capacitance of capacitor 1 plus the capacitance of capacitor 2. So this is to say that if I have two or however many capacitors in parallel with each other, to find their equivalent capacitance, all I have to do is sum the capacitances, which is super easy and nice. Okay, so like if you're trying to figure out like what's the equivalent capacitance of like multiple capacitors that are in parallel with each other, you just have to sum them. Okay, so let's look at this example. You have two parallel plate capacitors with the same distance D. One has area 1, the other has area 2. You connect them in parallel. What is the equivalent capacitance in terms of D, A1, A2, and any other relevant things? Okay, so let's draw out this like configuration. So this is just like, I've got two capacitors, capacitor 1, and I connect it in parallel to capacitor 2. So this is C1 and this is C2. Okay, the area of that plate is A1, the area of that plate is A2, and they have the same separation, right? D, the same distance between the two plates. Okay, so because these two plates are in parallel, which means that the voltage has to be the same across both of them, we can say that the equivalent capacitance is just the sum of each of the capacitance of each of them. Okay, so I can sub in, so now I'm going to remember the other definition of capacitance is just E naught times A divided by the separation between the two plates. So I can, I'm going to substitute that into each of these expressions for capacitance. So this is going to be E naught times A1 divided by D plus E naught times A2 divided by D. And D is the same in both cases, so I don't have to say D1, D2. So the equivalent capacitance is just going to be E naught times A1 plus A2 over D. Okay, so now that we've looked at capacitors in parallel. We're going to look at the other situation of how capacitors can be connected together. Like there's really only two cases, parallel and series. So now let's look at series. So we're going to draw a circuit that shows two capacitors in series. Um, these capacitors both start out uncharged, and when they are charged, they'll have the same Q. And the same and not the same. The total potential difference across them will be the sum of each of the potential differences. And then what we want to know is what is the equivalent capacitance if we were to reduce these two capacitors down to just a single capacitor. So let me draw out the circuit first. So let me start with a battery. And then this is connected to capacitor 1 and capacitor 2. Okay, so this is capacitor 1, capacitor 2. Okay. So how series is different from parallel is series and again, we're going to talk much more about this next week, but you have current. The symbol for current is capital I. Current is just the flow of charge. Okay, so you have current flowing to the capacitor and um and then going back to the battery. Okay. How a series configuration is defined is that all of the current that goes through one component goes through the other. Okay, there's not like a branching like there is with parallel. Again, this part is not as important. We'll go over all of this next week, but just know that this is what two capacitors that are connected in a series looks like. Okay, so there's going to be, so remember, this is the positive terminal of the battery and this is the negative terminal of the battery. There's going to be an accumulation of charge as like, so basically charge is going to flow through the wire and is going to accumulate on this plate. Okay. And charge is going to flow from this plate, from this bottom plate here, back to the battery, back to the negative terminal of the battery. Okay, so what will happen here is that will leave this plate negatively charged. The bottom, so like basically the top outermost plate will become positively charged because positive charge is flowing to that battery. And then you can think of it as like positive charge is flowing from this bottom plate back to the negative terminal of the battery. And it's leaving like a deficit of charge on this bottom plate, and that's why it becomes negatively charged. Okay, and so what happens to the middle, to these middle two plates? Well, those are electrically isolated, right? There's it's just basically like the bottom plate here, and then a wire, and then the top plate of this one. Okay, so what happens here is these plates become kind of polarized, opposite to whatever the plate above or below it is. So like the positive plate of this capacitor polarizes, like this whole middle section is electrically isolated, and it's also neutral. So it polarizes under the influence of the two plates on the outer, like the two sort of outer plates. So the positive plate up here causes this negative plate, like an accumulation of negative charges on the bottom plate of that first capacitor. And then because there are negative charges down here, right? Because there's charges going back to the battery and leaving that bottom plate negatively charged. This top plate here will become positively charged. Again, just due to polarization. Okay, so that's sort of like why you get the charge like separation on the two plates when they're connected in series. Okay, so but that's not really the question that we're asked. The question that we're asked is if I wanted to reduce these two capacitors just to a single capacitor, like if I wanted to have a circuit that looked like just this with a single capacitor, okay, just CEQ. Like, how would I add these two C1 and C2 up? How would I like what would I do to get those to basically reduce these down to CEQ? Okay. So we're going to start with the fact that on the equivalent charge on this CEQ is going to equal the charge on each of the two plates. Okay, and that is simply because the current is the same. Okay, so like the current going from like the positive terminal of the battery and back to the negative terminal of the battery is the same. And therefore, you're going to have the same like magnitude of charge on each of these plates, right? There will be like a plus Q charge on that top plate, and then a negative Q charge on that bottom plate, and then a plus Q charge on that top plate, and a negative Q on the bottom plate. Okay, so that there's you kind of start with this fact, the fact that the charge is the same. Okay. And I know because I'm told in the problem, but also it just makes sense that the potential difference of the battery, so say this is a 9-volt battery, is going to equal like the potential difference of capacitor 1 across capacitor 1 plus the potential difference across capacitor 2. Okay, so like whatever the potential difference across each of the two capacitors added together has to equal the potential difference across the battery. Okay, so the total potential difference across the battery has to be equal to the potential difference across capacitor 1 plus the potential difference across capacitor 2. Okay, now I know that the potential difference is just equal to the charge divided by the capacitance, right? That's basically the definition of capacitance just rearranged. And so I can kind of like write out the Q equivalent divided by the C equivalent, which is what I'm trying to which is what I'm kind of trying to derive here, is just equal to Q1 over C1 plus Q2 over C2. Okay, I basically just substituted like this in for that. Okay, and because I know that the Q's are all the same, these cancel. So this is to say that 1 over Q or over the equivalent capacitance when I'm adding capacitors in series is just equal to this. Okay, so that's sort of like deriving it for you. You don't have to derive it every time. You just know that like when you see two capacitors in series, they add in this way. Just like, you know, if you see two capacitors in parallel, they add in this way. Okay, so I just wanted to derive it for you once, so that you never really have to do it again once you've seen it once. Okay, so this question, two capacitors in series are initially uncharged. When we connect them to a voltage source, they both end up with the same charge. Why? Well, I've actually already explained this. I'll draw it out again, just um, sort of make sure it's clear. So basically, this question is asking why um, is the charge on each of these plates the same by definition when we have two capacitors in series? So the reason is that the current is the same when you have components in series, the current going from the battery has to be the same through both components. Um, and again, I've already explained this, but let me just try again. Just so sorry, I didn't mean to make that look like a capacitor. It's a battery. So this is the positive terminal of the battery. This is the negative terminal of the battery. So positive charge flows through this wire and accumulates on this plate. Okay. When enough charge has accumulated there, so that it's at the same potential as this terminal of this battery, charge stops flowing, and we say that the charge or that the capacitor is fully charged. So again, if this is a 9-volt battery, charge is going to accumulate on this top plate until you've got an equipotential surface all the way along like here. Okay? And then charge stops flowing and we say that the capacitor is fully charged. Okay. At the same time, positive charge is flowing back to the battery, to the negative terminal of the battery, right? It's flowing back like along this wire, and it's leaving a deficit of charge on that bottom on the bottom plate of the bottom capacitor. Okay, and it again flows until this whole surface is at the same potential. And again, if we have a 9-volt batteries, that would be like 0 volts. Okay, so like once you've got an equipotential surface with that whole bottom part, then the charge stops flowing. By definition, the amount of charge that builds up on that plate has to be the same as because it's the same potential difference. Okay. And again, because this middle section, these two plates here are isolated and neutral, they basically just get polarized so that they have the equal and opposite charge of whatever it is that's causing them to polarize, which is like the other plate, right? So you've got like this one becomes polarized positive and that one becomes polarized negative. So so that is why they both end up with the same charge. Okay, because the outer plates get equal but opposite charges from the battery. Okay, and the middle inner plates are electrically isolated and neutral, and they get equal and opposite charges sort of induced from polarization by their adjacent outer plates. Okay, so again, like I've this is sort of repetitive, but just I mean it's an important point. Okay, so this is another problem just to sort of like pull everything together with capacitors in series. So you've got two parallel plate capacitors with the same area. One has a distance of D1, the other has a distance of D2. You connect them in series. What is the equivalent capacitance in terms of A, D1, D2, and any other relevant constants? Okay, so let's draw it. For me, even though like I mean, it's like relatively easy to visualize. I always have to draw it. Um, okay, so this is C1, this is C2, this is D1, this is D2. This is the battery. Okay, so that's the positive terminal, that's the negative terminal. And we first of all recognize that the two capacitors are in series. So we know that their equivalent capacitance has to equal 1 over C1 plus 1 over C2. I know that the definition of capacitance, one of our two definitions is E naught over the E naught times the area divided by the distance separating the plates. So I can just basically sub that in, right? So this is going to be D1 over epsilon naught times area plus D2. So this is going to be D1 plus D2. And I can just sort of like flip both equations, right? So this is going to equal epsilon naught times area divided by D1 plus D2. Okay, so that would be how you would calculate if you were asked for the equivalent capacitance of two capacitors in series. Okay, so here's a summary of basically like, you could reduce like everything I've just said down to two equations. When you have capacitors in parallel, their capacitances just add. Okay, for the reasons that I've derived. If you just take away one thing, it's just this page that really matters. So like in parallel, capacitances add like this. In series, it's their reciprocal capacitances that add for reasons that I just derived for you. Okay, and that's the end of part 2. In the third part, I'll talk a little bit about energy and dielectrics.